Hello and welcome to the Unit 2 podcast on section 6.3. Today we're going to be discussing periodic trends for elements on the periodic table. I'm Mr. Sakaguchi.
And I'm Mr. Lin.
And let's start. So one of the, if you're going to have periodic trends, you have to have properties that you're going to look at. One of the properties we're going to be looking at is atomic radius. Now if you think about it, remember the radius is from the nucleus to where the electrons end, and because of the probability model for atoms, there really isn't a specific end to the atom because of the probability factor in the quantum mechanical model. So kind of keep that in mind.
So when we're talking about the atomic radius, we're talking about approximately mostly where the electrons are ending out. So it's just an approximation.
For metals, we define this as half the distance between nuclei, and then basically same idea for our for non-metals, same kind of idea.
You'll notice that as it goes from left to right, the atomic radius gets smaller, and then as you go down a group, it gets bigger.
Now the reason why it gets smaller from going left to right is because of increased nuclear charge. The idea here with nuclear charge is that you're adding protons to the nucleus as you go from left to right across the period, but when you add electrons, you're not adding new layers of electrons, you're basically adding electrons to the same energy level, and because of that, the positive charge will draw in those electrons closer and closer as you approach the end of the period.
So the nucleus is getting stronger, the center is getting stronger, but the electrons, even though you're adding more electrons, does not make the electrons any more powerful. So they're just getting pulled in.
Right. The group trend, the reason why you see the increase going from top to bottom is because of a phenomenon known as electron shielding. The idea is as you go down the periodic table, you get more and more layers of electrons.
Like an onion.
And outer layers are hindered from being attracted to the nucleus because of the inner layers of electrons kind of pushing it away at the same time. More layers, further away. And we'll talk more about this in class. Shielding, again, the idea here. If we're in the first level or first period, you have one shield of electrons. In the second period, quantum level, you have another layer. And if we're just pretend this third layer is in here for right now, the second layer has the pull of the nucleus drawing it in, but this inner layer from the first principal energy level is pushing it away. So you can imagine as more and more layers, you have more and more inner layers acting upon it.
So a way to look at it is kind of like saying, you're wearing in cold weather more layers of clothes. So as you wear more layers of clothes, your radius of your person gets bigger and bigger. Same idea.
In terms of nuclear charge, again, the principal energy level stays the same. Each element has, you add a proton, and the electron is in the same subshell. And again, same idea as before. No additional electrons are shielding those newly added electrons from the nucleus, and so pulling closer occurs.
It's pretty much, I think we've said it all.
Okay.
Yeah.
We can also talk about ionic radius. Remember, we have two kinds of ions to be aware of. Some elements will lose electrons and become positively charged. Other elements will gain electrons and become negatively charged. Positively charged ions are known as cations. Negatively charged ions are known as anions. Not cations, not anions. Okay. What we find is that if we compare ions to their element that is neutral, notice how the positive ions are always smaller than their elemental counterpart, whereas negative ions are always larger. Okay.
And the reason for this is because if it becomes more positive, that means it lost an electron, so it shrank in size. And then if it's an anion, that means it's gaining electrons, and that means you're adding another layer, and it becomes larger. And this trend also continues down a group due to more of that electron shielding.
Right. So think of it as like a tug of war. So you have, remember, the number of protons in all of these guys stay constant, right? if I'm losing electrons, now I have more protons than electrons, so the tug-of-war favors the nucleus, and so the nucleus pulls in the electrons that much more closely. For anions, you now have more electrons than protons, so now the extra electron side wins the tug-of-war, so it expands in size. And again, the periodic trend as we go from left to right decreases. Same reason as the atomic radius decreasing. Also keep in mind that there will be a jump as you switch from metal to non-metal. So when we're talking about these trends, we're talking about within the same charge.
Right.
The group trend is as you go down, the radius of the ion increases.
And this affects both cations and anions the same way.
Right. In terms of ionization energy, this is the third property we'll look at. Ionization energy is the energy required to move an electron from a gaseous atom. And there are different ionization energies. If we remove just one electron, this is known as the first ionization energy. If I remove an additional electron, that would be the second ionization energy, third ionization energy, and so on.
Realize it becomes more and more difficult as you remove more and more electrons because that nuclear charge is remaining constant, and therefore the pull on the individual electrons becomes stronger as you go.
So here we're looking not at the group or periodic trends yet, but just successive ionization energies going from first, second, third, fourth, and so on.
If you take a look at the numbers, we'll just use magnesium here, the second element, as an example. You'll notice it's 736, and then the second ionization energy will be 1445. It doubles. But then when you get to the third ionization energy, it more than multiplies by 5 or 6, something like that. So there's a huge jump between the second and third ionization energies. And this has to do, again, with that nuclear charge.
The idea here is there's a correlation between the number of valence electrons and the ionization energies. So sodium has one valence electron, so it removes remove the first electron, which would be the valence electron, is relatively easy. But when you try to remove a second electron, there's a huge jump. And the reason why you see that jump is because of the stability of the +1 sodium ion. For magnesium, remember magnesium has 2 valence electrons, so notice for the third one you see a huge jump. Aluminum has 3 valence electrons, so for the third one you see a jump. Silicon has 4, 5, and so on. So what we see here is a strong correlation between the valence electrons present and the ionization energies. More specifically for metals, less for nonmetals. I mean, you still see the trend, but the point is for the metals, it gives us a partial explanation for why sodium always forms a +1 ion and never anything else. You can see that it's energetically unfavorable for these elements to go beyond losing their valence electrons.
Right. So it's not impossible. It's just very, very unlikely because it just doesn't make sense energy-wise.
If we look at the trends for ionization energy, as we go across the period, it generally increases. There are some places where it decreases, but that's more of some subtle electron configuration issues. And if in AP we talk about it in more detail, but not at this level. The group trend is that we see the ionization energy decrease from top to bottom. Now, the idea here is that the reason why we see an increase from left to right is because nonmetals tend to not ionize by losing electrons. They tend to ionize by gaining electrons. If we go back a few slides to this one, notice how these are all negatively charged. So nonmetals generally will gain electrons to ionize, whereas metals will lose electrons to ionize. So this is why you see the increase, because it kind of goes against their character to remove electrons from nonmetals. That's why you see a steady increase. I mean, you can also argue that the nuclear charge increasing is an issue as well. The group trend, as it decreases from top to bottom, shouldn't be too surprising given the electron shielding stuff we talked about earlier with atomic radius.
Right.
So knowing what we know now, we can introduce the octet rule. The octet rule basically states that elements will tend to lose or gain or share electrons in order to acquire a full set of 8 valence electrons. Now this is true for the representative elements. The transition metals don't always do this.
They don't always follow that, drummer. So the octet rule actually was hinted at by John Newlands beforehand, and this is the real reason of why that his observations seem to work. The reason for this is because when you do the electron configuration, it'll show up that when you fill up to the 2s2, or sorry, the s2s and the p6s, when they get completely filled up, then that energy level has been fulfilled. And as a result, that's the most stable state for an element. So these elements are all going to try to get the most stable energy state, and they're going to either gain electrons to get to 8 or lose electrons to go to the next lower energy level. At the lower energy levels, 8.
The guidelines to kind of help you is these elements will tend to behave in a way like noble gases, and basically whatever noble gas is closest to that representative element is basically the way it'll behave. So notice how sodium has 1 extra electron than an S2P6 configuration, which represents a noble gas, right? So it's easier to lose 1 electron to mimic a noble gas configuration, which represents great stability. So this is why sodium becomes a sodium ion in this fashion always, by losing 1 electron. Fluorine, it's only 1 away from being like a noble gas, so it will always stabilize itself by gaining 1 electron, and that's why fluorine, when it ionizes, will always have a -1 charge, because it has 1 extra electron than it normally has.
So to do a quick way of just solving these kinds of problems, what you do is you look at the highest energy level, and if it's closer to 0 or 8, you can either gain or lose electrons. So the highest energy level, for instance, for sodium is 3s1. There's only 1 electron that's closer to 0, so it's going to lose that electron and winds up with the electron configuration underneath. And then with the fluorine, the highest energy level here is the 2 series, and that's got your S2 and a P5. That totals up to 7. That's just 1 away from 8. So it's going to gain an electron instead. And this has to do with those ionization energies.
Just remember that metals lose electrons and will become positive. Non-metals will gain electrons and become negatively charged. And we'll talk more about the logistics of this stuff. Electronegativity is the last trend we'll look at for the periodic table. Electronegativity is basically when an element is in a bonding situation, its ability to attract electrons that are being shared.
So they're unequal sharers in a way of looking at it, if one element is more electronegative than another. And this is the tendency for it to, in a bond, to attract the electrons more strongly towards its side.
All bonding is based upon differences in electronegativity. If we have tremendous differences in electronegativity, we end up with positive and negative ions like this. If we have an intermediate difference in electronegativity, we have something known as a polar covalent bond, which we'll talk more about. I know some of you probably remember hearing of this in your biology classes. And then the last one, if it's equal or about equal or 0 to no difference in electronegativity, then it's a nonpolar covalent bond. We can actually numerically quantify these. There are units known as Paulings that are used to measure electronegativity units. Noble gases do not show up in this trend because they don't form bonds with anything, so there's nothing to measure. And basically, the greater the electronegativity an element has, the more strongly the electrons will be drawn towards it when it forms a bond. So you'll see that highly electronegative elements tend to be negatively charged ions under the right circumstances.
So after discussing electronegativity, you'll see that there's also a trend for that across the periodic table, and it tends to increase in electronegativity as you go left to right, and also increases as you go from bottom to the top, okay? Or as it says here, decreases from top to bottom. That's about it.